In the last lecture of elasticity, we had discussed about strain, types of strain, Hooke's law, modulus of elasticity, then what are different types of elastic constants, and those elastic constants we discussed already are Young's modulus, formula for it we studied as mgl upon pi r square L. Formula for bulk modulus we discussed in the last lecture, and it is V dP by dV. Formula for modulus of rigidity is F divided by A into theta. All these formulae we derived yesterday in the last lecture of elasticity, and we know that this Young's modulus is the property of elastic solids, and Young's modulus measures the resistance offered by these elastic solids to elongation as well as compression. This bulk modulus is the property of solids, liquids as well as gases, and this measures the resistance offered by these solids, liquids or gases to change volume. This is modulus of rigidity, and this modulus of rigidity measures the resistance offered by solids only to change in shape. So all these things we discussed in the last lecture of elasticity. Now in this lecture we are going to discuss next point, that is stress strain curve. So what is there in the stress strain curve? Now, as the name is there should be a graph between stress and strain. On the y-axis we should take stress, on the x-axis there should be strain. Now for that we have to consider one wire again, metallic wire is there, and to this free end of the metallic wire we are applying loads in the steps there. One end of the wire is fixed to the rigid support. To the another free end we are applying loads in the steps, and after application of these loads in the steps we have to measure corresponding extensions, elongations, and this force, applied force, means stress, indirectly it is stress, that is F by A, and strain, that is elongation, divided by original length. We have to record these data, and according to this data we plot a graph. Means for different stresses we are measuring different strains, we are determining different strains for different stresses, and from that data on x-axis we take strain on x-axis, and on y-axis we take stress. Now at first when we increase applied force in steps, at first from point O to point A, what happens from point O to point A? We are observing that graph is a straight line. It means stress is directly proportional to strain in this portion. Stress is directly proportional to strain means Hooke's law is obeyed in this portion of the graph. Hooke's law is obeyed, stress is directly proportional to strain, and changes are reversible. What it means? It means that if we point A which is applied to the wire, then that wire regains to its original dimensions, or it comes to its original position there. And slope of this line OA is nothing but stress by strain, delta y by delta x, you know that, and it is stress by strain, and it is, because we are taking deformation in length, it should be Young's modulus. Now this is what all about portion OA of the graph there. It means at start, as we increase loading steps from point O to point A, the graph is a straight line and stress is directly proportional to strain. Hooke's law is obeyed, changes are reversible. Means if we remove deforming force, then that wire can regain its original dimensions. And we say that this is straight line portion of the graph and Hooke's law is obeyed here. Now, after point A, if we apply stress, strain will increase there. And in this portion AB there, we get portion AB of the graph there, and in this portion AB, what happens? Now, stress is not directly proportional to strain. Stress is not directly proportional to strain in the portion AB of the graph. It means Hooke's law is not obeyed in the portion in the portion AB of the graph. Stress is not directly proportional to strain and Hooke's law is not obeyed. But the wire has elastic nature and changes are reversible. Means again if we remove deforming force applied to the wire there, that wire comes to its original position, that wire regains its original dimensions, and we say that this point B up to which this wire regains its original dimensions after removal of deforming force, point B is called elastic limit. For that, point B is called elastic limit. Or this point B is also called as yield point. Point B is also called as yield point. Now, we can also say that the maximum stress at this point B is called elastic limit. Now, this point A is called limit of proportionality. Limit of proportionality means in this portion OA or up to point A, stress is directly proportional to strain. Limit of proportionality. This point A is called limit of proportionality and this point B is called elastic limit or yield point. Means from point O to from point B, wire has elastic nature. And that's why this portion OB of the graph is called elastic region. Because in this portion, what happens? This wire has elastic nature. Whatever may be there, stress may be directly proportional to strain, stress may not be directly proportional to strain. But in this portion, as wire has elastic properties, and that's why this portion OB of the graph is called elastic region there. Now what happens after this point B? Again, after point B, stress is increased in steps. We are increasing load in steps there. Strain is again increases, strain also increases there. And now Beyond this point B now, what happens? As stress is increased, strain also increases. And somewhere at point C, suppose we take point C here, and somewhere at point C, what happens here? At point C, wire has not elastic nature now. Beyond this point, elastic limit is finished. And after this point B, wire has not elastic nature now. And suppose we consider this point C, then at point C, what happens? That wire, if we remove deforming force, has some permanent strain. This permanent strain remains in the wire continuously. Means at point C, this wire has set or it has some permanent deformation, and we say that wire is in plastic deformation. Means what happens? If we remove deforming force at point C, the wire which is elongated does not regain its original dimensions completely. It has some permanent strain. Suppose wire is of 5 cm long and we are at point C. Then what happens? Elongation produced in the wire is, for example, 1 cm. And if we remove deforming force, this elongation 1 cm does not remove. The wire has permanent deformation, permanent strain, that is of 1 cm in the wire there. So in this case, in this way, if we remove deforming force at point C, the wire has some permanent strain. So this portion O dash is called permanent strain, or it is also called as set. And we say that wire has plastic deformation. We know plasticity. What is plasticity? What is plastic deformation? If the deformation is in the wire, after removal of deforming force, that wire does not regain its original dimensions. Whatever is the change there, that remains permanently in the material. This happens here only. Means now instead of going to position O, this wire goes to position O dash. Means this wire, after removal of deforming force, does not regain its original dimensions. It has some permanent strain that is set, and we call wire has plastic deformation. This is the case. Now, beyond point C, what happens? As the stress is increased by a small amount, strain increases by more amount. Beyond point C there, what happens? We are increasing load in the steps continuously, and as the stress is applied, stress applied by small amount, strain increases large. Means small increase in stress causes large increase in strain after point C. Now this happens up to point D. We are increasing stress. See, we are increasing stress and strain is also increasing there. And after this condition now, after this position, point D comes, and at this point the wire has some stress, and that is maximum stress this wire can bear, which is called breaking stress. Means the stress at point D which wire has is maximum stress that wire can bear. Beyond that, wire cannot bear a stress, even a small stress. If we apply a small stress, after this wire will break. And that's why this is the limit. This is the stress, maximum stress that wire can bear, and which is called breaking stress. Now this portion, now you know that up to point B elastic limit is there. After point B elastic limit is not there. Wire is in plastic deformation, and from point B to this point D, wire is in plastic deformation. Means if we remove deforming force, wire does not regain its original dimensions, and wire is said to be plastic deformation. That's why this portion B to D of the graph, portion B to D of the graph, portion B to D of the graph is called plastic region. Portion B to D of the graph is called plastic region. In this, wire has plastic deformation. It means wire does not regain its original dimensions after removal of deforming force. So D is breaking stress, point of breaking stress, or the stress at point D is called breaking stress. Now what happens beyond point D? Now beyond point D, even if stress is removed, the stress applied to wire is removed, wire starts elongating continuously beyond point D. Even if stress is removed, wire starts elongating continuously, and we say that wire starts to flow as a liquid. Beyond this point D, wire starts to flow continuously, and a neck is formed in the wire. Thinning of wire increases. Neck is nothing but the portion at which diameter of the wire becomes less than, and finally at point E, wire breaks. So this portion, so this point E is called fracture point. It can also be called as a rupture point, or it is also called as breaking point. So this is behavior of the wire under increasing load. As we increase load in steps, the wire behaves like this. Now this is the nature of the stress strain curve for materials like copper, like iron. But we take different materials. Whole portion of the curve or whole portion of the graph may be there or may not be there in the stress strain curve. Means for different materials, the nature of the graph, nature of stress strain curve may be different there. So we repeat the things in short there. What happens? There is a metallic wire. We are applying load to this wire in steps there. And as we apply load in steps, means we are changing stress and we are determining strain, corresponding strains there. We have data, stress and strain. We have some observations of stress, we have some observations of strain. And if we plot a graph of stress versus strain, the graph is like this, curve is like this. Initially what happens? Initially the graph is a straight line up to point A. This is original position, position of the graph, position of the wire, and from point O to A, the graph is a straight line. What it means? It means that during this portion, as we increase stress, strain increases, but stress is directly proportional to strain. Means as we increase stress, in proportion strain also increases there. And slope of this line will be constant, etc., etc. And this point, in this portion, Hooke's law is also obeyed. Stress is directly proportional to strain. Changes are reversible. Means if we remove deforming force, that wire regains its original dimensions, etc., etc. And this point A is called limit of proportionality. Up to this point A, these things happens there. Now, from A to B, beyond this point A, we are again increasing stress. Strain also increases there. somewhat different there. From point A to B, stress is not directly proportional to strain. Hooke's law is not obeyed, but wire has elastic nature. It means that if we remove deforming force, wire regains its original dimensions. These all things happens from point O to point B. From the portion O to B of the curve, these things happen there. And this from point O to from point B, we say that wire has elastic nature, and this point B is called elastic limit or yield point. Means up to this point, wire has elastic nature, and that's why this portion OB of the graph is called elastic region. Now what happens beyond this point B? Beyond this point B, we are increasing stress in steps, and strain also increases. But wire has not elastic nature now. And from point B to, we say D up to D, continuously we are applying stress, then strain also increases. And suppose in between this B to D, suppose there is a point C. What happens at this point C? At this point C, if we remove deforming force, that wire has some permanent elongation. And that permanent elongation is called permanent strain. And if we remove deforming force, this wire has permanent strain, and wire does not regain to its original dimension. Means, instead of coming to O, this wire has position O dash. And this O dash is called permanent strain or set. And we say that wire has plastic deformation. Understood? After this point C, for small increase, we are increasing stress in steps there. For small increase in stress, there is large increase in strain. And this goes on continuous up to point D. And at point D, whatever that wire has a stress, maximum stress, that is called breaking stress, because this maximum stress wire can bear. If a small stress beyond this is applied to the wire may break there. And that's why this point D is called breaking stress. That is the maximum stress that wire can bear. Now, after this point B, wire starts to elongate continuously even if stress is removed from the wire. It starts elongating continuously, and we say that wire flows now, starts to flow now, because we know that liquid flows. And after this point D, we say that wire starts to flow. Means thinning of wire increases and a neck is formed in the wire. Neck means, I told you already, the portion having very small diameter that is formed in the wire means. And finally at point E, that wire breaks, and this point E is called fracture point or rupture point, or we can say it as breaking point also. So this is all about behavior of the wire under increasing load. I told you already that the materials like copper or iron have this behavior, and if we take some different materials, then these different materials have some different nature of the curve there, and it means that this whole portion or some portion may not be there in the stress strain curve of those materials. So this is all about your stress strain curve. And the most important thing is this portion B to D of the graph is called plastic region. This portion O to B of the graph is called elastic region. In this portion, wire has elastic properties. In this portion B to D of the graph, wire has plastic properties, or we can say it has not elastic properties. So this is all about your behavior of the wire under increasing load. Now from this, we are going to discuss some types of substances. And firstly I will discuss ductile substances. What are ductile substances? So the substances which have more plastic region. Plastic region in these substances, plastic region is greater. In ductile substances, plastic region is greater. And they have small elastic region, means elastic region is small. Examples of these substances are copper, iron, etc. Now plastic region is greater means B to D portion is greater in these substances and elastic region is small means O to B region is small. What it means? It means that if we apply some deforming force to these substances, they lengthen considerably. And after they have plastic deformation and then they break. Means at first they will lengthen, then they have plastic deformation, then they break. And that's why if we have to make some wires, metallic wires, we use these substances. So these are ductile substances which have more plastic region. Another type of substance is brittle substance or brittle substances. Brittle substances, example of this is glass or ceramics, we can say. Here I will write example of this as copper or iron. Here I write example of this as glass. Now what happens in case of brittle substances? In case of brittle substances, plastic region is small. Plastic region is small and elastic region is greater. Elastic region is greater. Means these substances break within elastic limit only. You can understand how is the nature of glass there. And that's why these substances, they break within elastic limit only. They have elastic region and plastic region, their plastic region is small. So if we apply some deforming force, what happens? They can break within elastic region only. So this is all about brittle substances. Again, we have another type of substance, that is elastomer. What are elastomers? Best example of this is rubber. And in rubber, no plastic region is there. No plastic region is there. And they have only elastic region. They have only elastic region. It means in this plastic region is absent totally. They have only elastic region. So these substances like rubber, they can lengthen many times, comparatively many times than their length. We can understand. If we apply some force to the rubber, what happens? It lengthens many times more than its original length. And those substances are called elastomers because they have no plastic region. They have only elastic region, and best example of elastomer is rubber. So these are some, there are some malleable substances also. If we want to make sheets, for example gold, silver, etc., then we can use these malleable substances. So from those malleable substances, sheets can be easily prepared there. So all these about types of substances. I repeat, in short, ductile substances, examples are copper, iron, etc. Plastic region is greater in ductile substances and elastic region is small. They lengthen considerably and then they have plastic deformation and then they break. Brittle substances, example of brittle substance, best example of brittle substance is glass, or we can say ceramic. Ceramic also example of brittle substance. So in this, plastic region is small and elastic region is greater. And third type we discuss as elastomers. So what are elastomers? Elastomers, we put example of rubber in front of us. So rubber has no plastic region, it has only elastic region, and it can lengthen in large amount by its original length. So this is all about your stress strain curve and types of substances, etc. etc. So I think you understood all these things. So this point is limit of proportionality, this point is elastic point or yield point, this point C, at this point D. At this point C, wire has plastic deformation, permanent strain is set up there, and D point is called breaking stress and point E is called breaking point. So this is stress strain curve. Okay. So from the last lecture, actually we have knowledge of bulk modulus. What is bulk modulus? Bulk modulus, we represent it by symbol K, and it is V dP by dV. So from this, we explain another thing, that is compressibility. What is compressibility? Compressibility is reciprocal of bulk modulus. That is 1 by K is called compressibility. So 1 by V dt by dV is compressibility, and it is equal to V dP, it is equal to dV by V dt. What is SI unit of this compressibility? SI unit of this compressibility is, as we know that SI unit of bulk modulus is Newton per meter square or Pascal. So SI unit of this compressibility is meter square per Newton, or we say that Pascal raised to -1. And dimensions of this compressibility are, actually we know dimensions of stress, we know dimensions of bulk modulus. Dimensions of bulk modulus are m1, L -1, T -2. So we put all these into denominator, and we have, these are dimensions of compressibility. So as bulk modulus is the property of gases, liquids and solids, this compressibility is also property of gases, liquids and solids. So this is your, what is dV? It is change in volume. What is V? It is original volume. We already studied that rubber bladder, and this rubber bladder, if we are applying forces from all sides, then volume of this rubber bladder decreases to dV. V is the original volume, and final volume of this is V minus dV. If we are applying forces from all sides, then bulk modulus is V dP by dV. V is original volume of that rubber bladder, dP is change in pressure, actually what is dV? Change in volume, and reciprocal of all these things is called compressibility. So there are some numericals, there may be some MCQs from this term compressibility in the exam. So all this is about compressibility. Now after that, we are going to discuss one another point, that is Poisson's ratio. Poisson's ratio, which is represented by letter sigma. Again, symbol may be different in different books there. Poisson's ratio. So what is Poisson's ratio now? Now again take example of metallic wire. and to this metallic wire apply some force there. Load you are applying means force you are applying to the free end of the wire there. Now when you are applying some force or load to this wire, to the free end of this wire has some radius, for example R, and diameter of this wire is suppose D, and original length of the wire is, for example, L, and this wire has cylindrical nature. Now when we apply some deforming force to this wire, what happens? Wire gets elongated, and at this time there is change in length of the wire, but at this time there is change in diameter of the wire also. As length gets increased, diameter of the wire goes on decreasing there. You can imagine when length goes on increasing there, diameter of the wire goes on decreasing, and then related to all these things means there are changes in length and there is change in diameter. There is change in length of the wire as well as there is change in diameter of the wire also, and related to these things means changes in length and changes in diameter, or change in length and change in diameter. We have another ratio, we can define another ratio, that is called Poisson's ratio. This Poisson's ratio is actually ratio of lateral strain to longitudinal strain, or linear strain we can say. So what is like, we observe that there are changes in two ways. First change is in length, another change is in diameter. We have to consider both the changes in this case. And as there is increase in length, there is decrease in diameter, and increase in length and decrease in diameter, both things if we relate, then we have one ratio that is called Poisson's ratio, and this Poisson's ratio is nothing but the ratio of lateral strain to longitudinal strain. This is nothing but Poisson's ratio. So what is lateral strain? Whenever there is change in diameter, when there is change in diameter, we are saying that there is change in diameter also, diameter goes on decreasing. When length increases, diameter decreases. And by other side, when length decreases, means if there is a compression, then diameter of the wire increases there. So what is lateral strain? When there is deformation in diameter of the wire, then the related strain is called lateral strain. Means when changes in the diameter of the wire are there, that is lateral strain. What is longitudinal strain? We know that whenever there is change in length of the wire, the strain is called longitudinal strain. Means this longitudinal strain is there when deformation is in the direction of applied force, and lateral strain is there when deformation is perpendicular to the direction of applied force. There is change in diameter means deformation is perpendicular to the direction of applied force. We are applying force in this direction. And there is change in diameter means deformation is perpendicular to the direction of applied force, and there is change in length means deformation is in the direction of applied force. So related strains are lateral strains and longitudinal strains. So what is lateral strain? Lateral strain is the ratio of change in diameter to original diameter. And what is longitudinal strain? Longitudinal strain means the ratio of change in length to original length. Now in this case, what is original diameter? Original diameter is for lateral strain is equal to, we say that lateral strain is equal to change in diameter divided by original diameter. So what is change in diameter? Suppose change in diameter is small d. So small d upon capital D is lateral strain. And what is longitudinal strain? Longitudinal strain is equal to change in length change in length upon original length. Now we know that change in length when we apply some force here is small l. And small l divided by capital L. Capital L is original length, change in length is small l, and small l by capital L is longitudinal strain. So we put these values of lateral strain and longitudinal strain into this formula for Poisson's ratio, and this is equal to small d divided by capital D divided by small l by capital L. It means it is equal to small d into capital L divided by L into capital D. So this is your Poisson's ratio. So Poisson's ratio, in Poisson's ratio we observe that in the denominator and in the numerator lengths are there. Diameter, length, diameter, and that's why it is unitless as well as it is dimensionless. It has no dimensions as well as it has no unit. So this is Poisson's ratio. So what is Poisson's ratio? It is the ratio of lateral strain to longitudinal strain. Lateral strain is change in diameter to original diameter. It is change in diameter divided by original diameter, and longitudinal strain is change in length divided by original length. So finally Poisson's ratio is d by d divided by L by L. L is original length, change in length is small l, so capital D is original diameter of the wire there, and small d change in diameter there, small l is extension or elongation produced in the wire, and finally we got Poisson's ratio as dl by lt.